Okay, so now let's move to Carnot's theorem, and it's written here, really remarkable result by Sadi Carnot. And you could argue to a large extent that the entire theory of thermodynamics was shaped because of the contents of this theorem. So to a large extent, not entirely, but to a large extent, that is true. So let's see what the theorem says. It's written here. Main statement is the thermal efficiency of any arbitrary heat engine which operates between two temperature levels, so that is between two heat baths, or maybe between more than two heat baths, but in the end of the day only two heat baths actually matter, like we saw before with the Ericsson cycle or the Stirling cycle. So this thermal efficiency cannot be larger than the efficiency of a reversible engine cycle which operates between those same temperatures. Okay, very deep and general. We're going to see exactly what that means in a moment. But a immediate consequence of this is that all reversible engine cycles which operate between those same temperature levels fixed must necessarily have the same thermal efficiency. Okay, regardless of the cycle, regardless of the working substance, regardless of everything. And then finally this efficiency, which is the maximum efficiency that any heat engine operating between two temperature levels can have, only depends on the temperature of the hot heat bath and the cold heat bath in some functional form. Okay, so let's see how we can prove this. And to do it, let's consider that you have a heat bath here. So this is a temperature T hot, and another heat bath down here, which is a temperature T cold. Okay, and of course the name tells you already that T hot is larger than T cold. Okay, and we are going to have here two systems, two cycles. Let's try to draw a circle. That's it. This is going to be cycle 1, and I'm going to make cycle 2 sitting next to it here. Okay, so these are two cyclic thermodynamic processes. Sorry. Let's see if I can do it. Yes, there we go. So these are two cycle thermodynamic processes. I broke the hot bath, the cold bath, sorry. They are completely general, and the only thing I'm going to say is that this C1 is arbitrary, so it could be reversible or irreversible, but C2 is reversible. Okay, so that's the only thing I'm going to say. So note, in particular, I'm not saying which thermodynamic cycle is. Okay, so I'm not saying, for instance, that this C1, which is arbitrary, and maybe it's irreversible, and maybe it's the Ericsson cycle run in an ideal gas. I'm not saying any of this. The working substance can be anything. There could be changes of phase, it could be a liquid, it could be a gas, it could be whatever you want, okay? And the cycle, specifically that is running here, can be an arbitrary cycle as long as it operates between effectively two temperature levels, okay? And this other cycle here, I'm saying it's reversible, that's the only thing. So it could be, again, any cycle, and it doesn't have to be the reversible version of this cycle C1. It doesn't have to operate in the same working substance, the same gas. It's just another engine which happens to be reversible, okay? So I'm going to put these two guys there, and I'm going to make them work, okay? So this is an engine. It's running in the clockwise direction, and it's absorbing, therefore, some amount of heat. Q hot, let's call it Q hot 1, which is going to be positive because it's going into the system, and it's releasing some heat Q cold 1, which is negative. So let's just write it like that. So this we write it positive, this we write it negative. And as a result of the imbalance between these two heat fluxes, you get some work output, okay? So this work is going out, which means it is negative from the point of view of this cyclic process. And then what we're going to do is we are going to couple C1 to C2. So how do we couple it? In the sense that all the work that I'm generating from running C1, I'm going to deliver that work into C2. So from the point of view of C2, this work is going to be input, so it's going to be positive, And this cycle, which is reversible, I'm actually going to be running it as a refrigerator. So if you want, in the VP representation, that would be running in the counterclockwise direction. Okay, so like this. Don't like this arrow, let's make it better. Okay, so what happens when you run in the counterclockwise direction in the VP representation? Where you draw some heat from the coldest path, which is QZ, in this case is 2, which is different. In this case it's positive. And then you release that heat, well, not that heat, some heat, into the hottest bath. So Q hot 2. And this is heat released, so it's going to be negative from the point of view of cycle 2. Okay, fine. So that's the setup. And of course, these two things have some thermal efficiency. So in particular, it's important to note that C2 is reversible. Okay, so here I'm running it as a refrigerator. But because it's reversible, I know for sure that I can run it in reverse. So I could run it like that. And when I run it like that, I know because it's reversible, I know that I can take an amount of heat exactly equal to the absolute value of Q hot 2. I will be releasing exactly equal amount in absolute value of heat into the coldest bath. Okay, Q2. And as a result of this, I will be able to deliver some work, which is going to be negative and identical in absolute value to the work which is being fed into this reversible engine, just because it's reversible. That's what it means to be reversible, okay? So I can define a thermal efficiency for C2 when it's running as an engine, and for C1. And for that, I just apply the definition, right? So the thermal efficiency of the first guy is going to be equal to the heat that comes from the hottest source divided, sorry, this is not true, as you know, it's going to be equal to the absolute value of the work that is produced divided by the heat which is absorbed. And in the second case, we have the same thing, right? Because the work in this case is the same in magnitude, but the heat in this case is in principle different, so it could be different. I'm going to put it here in absolute value because it's sometimes negative or positive, so that nobody is confused. Okay, so that's the setup to prove the theorem. Now, what does the theorem say? The theorem says that the thermal efficiency of any thermodynamic cycle, eta 1, for instance, can never be larger than the thermal efficiency of a reversible cycle operating between the same heat sources. So what this is saying is that eta 1 is smaller or equal than eta 2. Okay, and emphasize or equal, because here it doesn't say it has to be smaller. It says that cannot be larger. Cannot be larger is not the same thing as it's smaller or equal. Okay, so that's important to put in there. So this is what the theorem says. Let's assume for a moment that this is not true, and you can have larger efficiency in an irreversible cycle. So what this implies, if you just look at the thermal efficiencies, is that W divided by Q hot 1 is larger, that's what we are saying, what we are supposing, than this thing. Okay, so this goes with that, and this means that Q hot 2 needs to be larger than Q hot 1. Okay, so what does this mean? When we go to the picture here, to the drawing, we see that this means that I'm taking some amount of heat, Q1, from the hot source, and I'm releasing back after I finish the entire cyclic process. So you have to think about this as a global process. So first you run one cycle of C1, and then you run one cycle of C2. And this combined cycle together is going to be your total cycle. And this is a cyclic process in which, in particular, the internal energy doesn't change because it's cyclic. So the whole thing, system C1 and C2, arrive both at the same initial state after you have run one cycle of each of them. Okay? So what we have done over an entire cycle is we have drawn some heat from the hottest source, and we have put more heat into the hottest source than we have drawn, because this guy is bigger than this one. Okay, so we are throwing in more heat than we took before. So overall, the net interaction with the hot source is to give out some source to it, some heat to it. Okay, and this heat that is being released is actually equal to Q1 minus the absolute value of Q hot 2, which is negative because it's going to the hot bath. And because of conservation of energy, because we have said, if you look at here, we have said that all the work being produced by C1 is entirely feeding the cycle C2. So there's no work being produced overall because these two cycles are coupled together. So there's no work. And the fact that the internal energy equals 0 in the entire cycle, remember the first law of thermodynamics, let's write in black so that you can see better. So the first law of thermodynamics tells us that heat plus work has to be 0 in a cyclic process in this case, but we're saying that there's no work, which means that the heat must be compensated. The heat that goes into the hottest source is entirely coming from the cold source, okay, because there's no other sources of energy involved in this process. And what we have just built is an impossible machine. Like you can see, it violates Clausius' statement of the second law of thermodynamics because we are taking a cyclic process that takes some heat from the coldest temperature bath and throws it into the hottest temperature bath. That's not possible. Okay, that's against the second law of thermodynamics, which means that this assumption that the efficiency of 1 can be larger than the efficiency of 2 is wrong. Okay, so we must have then what Carnot tells us, which is that the thermal efficiency of, let's make it in black again for consistency. So this thermal efficiency of any heat engine cycle, whatever it is smaller or equal than Carnot's efficiency. Okay, so that's important. Now, there is an immediate consequence of this, which is that all reversible cycles have the same efficiency. So how can we see that? We said just now that C1 was arbitrary. Arbitrary doesn't mean irreversible. It can be irreversible, but it could also be reversible. Why not? So what if C1 was also reversible? Then we can repeat the entire same reasoning, changing the labels 1 by 2. It's the exact same reasoning, but whenever we wrote 1, we now write 2. And what we arrive at is that the thermal efficiency of 2 needs to be smaller or equal than the thermal efficiency of 1. And the two things can only be simultaneously true if eta 1 equals eta 2, which means all reversible cycles have the same thermal efficiency. Okay? And another thing that you have to take into account is that, like I emphasize, I didn't say anything about the working substance or about the details of the cycle or anything at all. Okay, so what I'm saying is that if you have, for instance, an Ericsson cycle or a Stirling cycle or a Carnot cycle run reversibly, you know from Carnot's theorem, because these are all thermodynamic cycles that operate effectively between two definite temperature levels, they all have the same thermal efficiency. But this thermal efficiency cannot depend on the details of the cycle, because different cycles have the same efficiency, and it can also not depend on which substance do you have. If it's, for instance, a gas which is in the ideal gas limit, or if it's a van der Waals gas, or if it's a liquid, or if it's anything. Okay, so you really don't specify what it is, but you know for sure all of these things have the same thermal efficiency. You know, the only thing which is being fixed, which is being given by us, is the temperatures. Okay, that's the only thing we are specifying. So if all the reversible engine cycles have the same efficiency, then this efficiency, let's call it reversible, must necessarily be a function of the temperatures, T cold and T hot. Some function of them. I don't know which function, okay? To find out which function, we are going to say it later. And this efficiency of a reversible cycle, remember, it's the maximum efficiency that anything can have. Any efficiency is smaller or equal than this maximum. That depends universally only on the cold and hot bath temperature and not on any details of the system. Okay, so this is extremely general and extremely powerful as a result, and it has very important consequences. One of them, it allows us to define the absolute temperature scale, which we are going to see in a minute. So there's one section in the lecture notes that you will see under the heading of 524, where the thermal efficiency of the ideal gas Carnot cycle is worked out. And why we do that? Well, we don't know this function. All we know is that the thermal efficiency is the same for all reversible engines, regardless of what is the working substance. So we can fix the most convenient and easiest thermodynamic cycle we like, which is the Carnot cycle, and we can apply the Carnot cycle to the simplest possible thermodynamic system we like, which is the ideal gas. Any other system running on any reversible thermodynamic cycle between two given temperature levels will have exact same thermal efficiency because of Carnot's theorem. And this is the beauty of it, okay? So we can go to the simplest system and find out what this function of temperature is. We are going to do this in the synchronous session. You have it in the lecture notes, and what you find when you run the Carnot cycle on an ideal gas is that the thermal efficiency, which is by definition this thing, like we saw before, is 1 minus T cold divided by T hot. Okay, and this is absolutely remarkable result. Okay, so it's really simple expression, and you see that we were expecting this to be a function of temperature, T cold and T hot, and what we actually found is that the thermal efficiency is 1 minus some function of the cold temperature and some function of the hot temperature, and these functions are actually just proportional to the absolute thermodynamic temperature with some proportionality constant, which is arbitrary. Okay, so if you put some a here and a there, they will cancel out, so you don't know what the constant is. You are free to choose whichever constant you like. Okay, and this t that comes in here for us up to now is the temperature measured in the Kelvin scale. Okay, so this scale that we introduced given a specific value to the temperature of the triple point of water. Okay, so somehow it's a special empirical temperature that we just claim is the true thermodynamic temperature, and we see that that precise scale is the scale that comes up in the expression of the maximum efficiency of any reversible, or of any heat engine, as given by the second law of thermodynamics. So there's something really special about this scale of temperatures. We didn't get a different function here with some like constants and stuff. We just got the Kelvin scale temperature just like that, without any addition, without any power law or anything. It's just plainly the temperature in the Kelvin scale. So there's something really special about it. That's why we call it the absolute or the true thermodynamic temperature. Okay, so like I say, we are free to choose this constant, and this constant gives you the size of the degree. So what we do, just for historical reasons, is to fix the size of a degree exactly being the same as the size of a Celsius or centigrade degree. So we say that 273, we take all the range of Kelvin temperatures between what would be 0 degrees Celsius, which is 273.15 Kelvin, and we go all the way to 373.15 Kelvin, and we say that the divisions, the equal divisions of that scale are going to be coinciding with 1 degree Celsius by construction, because we take 100 degrees and we divide it equally, and we say that this thing here is 1 degree Kelvin, which is the same thing as 1 degree Celsius. Okay, it's just for historical reasons. So that's how we fix our proportionality constant. And this is how we have defined the temperature scale. So imagine, for instance, that this is completely impractical and nobody does this, but you could make a thermometer with a reversible engine, okay? Imagine you have an engine which is very close to being reversible, because we know this is an idealization, they don't exist. And imagine that you measure its thermal efficiency. You measure that, okay? And imagine that you know what the temperature of the hot bath is. Imagine that you know that, this is fixed. But then you can figure out what the temperature of the cold bath is, because you know this and you know that. And you have the formula for the efficiency of a reversible engine. Okay, so that's how you can operationally, if you like, define a thermometer that measures the absolute temperature scale. Okay, so this is the last thing of this chapter, and in the next chapter, next chapter is a self-study pack, but later we are going to see further consequences of Carnot's theorem, which is the introduction of entropy, and this will close the basic thermodynamics part of our course. So I will see you there.